When we look at the vastness of the universe, with its planets, stars, and space, a central question arises. Why is there something and not nothing? This puzzle becomes even more confusing when we consider the balanced laws of physics that govern our universe, where matter and antimatter appear to be equally balanced. However, we find from observation that the stars and galaxies we see are mostly made of matter, with almost no antimatter. It makes us think about the unpredictable forces that caused it to bend, revealing the universe as we see it. What remarkable mechanisms contributed to the situation, giving us a universe full of systems, stars, and the mystery of our own reality? Centuries ago, scientists believed that the universe existed in an eternal form governed by constant laws of physics. But in 1927, Belgian priest and scientist Georges Lemaitre proposed an alternative idea. He proposed that the universe began with a huge primordial atom that exploded and produced the smaller particles we see today. Despite initial indifference to his idea, the opinion of Lemaitre was supported by the 1929 discovery of the cosmologist Edwin Hubble of the expansion of the universe. After this discovery, scientists concluded that if the universe expanded, it must have started from a small, dense point. Astronomer Fred Hoyle aptly called that idea the Big Bang theory, which was later adopted by its proponents in the mid-1960s. Cosmologists Arno Penzias and Robert Wilson accidentally discovered evidence supporting the Big Bang hypothesis while trying to tune microwave signals from the Milky Way. They found a persistent background noise that turned out to be cosmic microwave background radiation, a remnant of the Big Bang. But how did the Big Bang lead to the formation of planets, stars, and galaxies? Through precise measurements and observations from ground-based telescopes and space probes, scientists have created a convincing explanation. About 13.8 billion years ago, all matter in the universe was created from a single point or singularity in a powerful burst of energy. This rapid expansion, called inflation, created space and natural forces. In fractions of a second, the energy was transformed into particles of matter and antimatter, most of which annihilated each other. Fortunately, a small amount of matter was conserved and eventually protons and neutrons were formed. Within minutes, these particles began to fuse together to form hydrogen and helium nuclei. Over time, the particles merged and filled the universe with gas clouds. About 380,000 years later, what remained was the cosmic microwave background, which contained small fluctuations of matter that later grew into galaxies and cosmic clusters. Our observations of the universe today, along with the progress of science, paint a consistent picture. Our universe is composed primarily of matter, obeys the laws of physics, and evolved over billions of years from a uniform sea of hydrogen and helium to an organized sea. The sea, a cosmos full of galaxies, stars, planets, and even intelligent life. This incredible journey from simplicity to complexity is a testament to the wonders of cosmic evolution and human wisdom. From today, we can trace back in time and study the origin of every single structure or part of the universe. With each answer we receive, we can appeal and ask how and where it happened, until we reach a point where our understanding fails us, where we are forced to admit that we do not know. Then we can reflect on what we know and ask how it came to be, wondering if it is possible that it could have come from nothing. The life we face today comes from the tiny particles that create everything around us. These particles act as building blocks that join together into the complex molecules necessary for life. Basically, these building blocks are atoms, the basic units that make up all the matter in the universe. However, atoms did not suddenly appear at the beginning of the universe. They went through a long process of formation. This process involves the life cycle of stars, birth, life, and death. As stars reach the end of their lives, they produce new materials through nuclear reactions. These materials promote the formation of new stars and continue the cycle. This cosmic recycling is crucial for the existence of planet-like celestial bodies and the complex chemistry necessary for life. For the universe to have stars and galaxies as we see them today, several critical factors must line up. Gravity played an important role because it grouped smaller celestial and cosmic groups into larger structures. In addition, the presence of dark matter in the early universe prevented matter from being lost to space during star formation. The delicate balance of different types of matter and radiation was important for phenomena such as the cosmic microwave background and the formation of galaxies. In addition, small fluctuations in matter density, which gravity had to be reinforced during long distances, were important in forming the structure of the universe. These primordial irregularities, along with the birth of dark matter and ordinary matter, laid the foundation for everything we see. Looking at the balance of matter and antimatter, the mystery deepens. Although physics naturally treats matter and antimatter equally, there is too much matter in our universe. Some factors could explain this difference, such as unique conditions during the formation of the universe, unusual processes that defy standard norms, or interactions that favor the formation of matter instead of antimatter. The standard model of physics includes these ideas, but does not provide a complete explanation. Dark matter also causes the problem. Although it is not composed of standard model particles, its presence is determined by several observations. The origin of dark matter is still uncertain, with theories ranging from its creation in the hot phase of the early universe to its formation through gravitational interaction. In conclusion, although we have made significant progress in understanding how the universe works, there are still many questions about its origin and composition. Exploring these mysteries drives research, pushes the boundaries of our knowledge, and inspires new avenues of research. There had to be a mechanism to create the energy necessary for the universe to exist if it didn't exist before. According to our theory of cosmic inflation, the leading universe before the Big Bang, this energy could have come from nothing. When we imagine the start of a hot Big Bang, we usually imagine a scenario of extreme heat, density, and energy. When we look at the manifestation of this state, we encounter two perspectives. First, we could simply say that the universe arose in this way with initial conditions, without further explanation, a position that some might describe as a capitulation to the realm of theoretical physics. Alternatively, we can take the more popular approach among theoretical physicists and formulate a hypothesis to explain these initial conditions. This requires making predictions that deviate from currently accepted theory and subjecting them to empirical testing. Last approach inflation changes our understanding of the origin of the universe. Instead of imagining a hot, dense beginning as an infinitely small, infinitely hot place, inflation represents a stage before the Big Bang where space itself experienced a very high energy density. This rapid expansion of the universe during inflation caused the conversion of energy into matter, antimatter, and radiation, leading to the hot Big Bang. Furthermore, inflation not only creates a universe characterized by uniform temperature and uniform appearance, but also predicts the particular density fluctuations observed.
From a state of energy-saturated, almost empty space, natural processes gave rise to the development of the entire observable universe, full of its numerous structures. While this idea provides a compelling framework for understanding the beginning of the universe, it may not satisfy everyone. Conceptualizing the concept of a universe without space-time and the laws of physics can be difficult. From a philosophical point of view, one could consider dimensions beyond space and time, or conditions that are not limited by physical reality. Scientifically, there are several ways to define nothing, each valid in its particular context. These definitions range from the time when nothing existed to the most empty space in space-time with the lowest energy. While some definitions may confirm that we evolved from an empty universe, others are more ambiguous. Ultimately, the question of a universe coming out of nothing lies at the limits of our current scientific understanding. Although quantum theory suggests the possibility of universes arising from quantum fluctuations, empirical evidence is still lacking. Thus, while the idea that our universe came from nothing is attractive, it requires further investigation and confirmation in theoretical studies. Donen. He and his team at the Wuhan Institute of Physics and Mathematics made a significant contribution, providing the first numerical confirmation that the Big Bang can indeed cause quantum fluctuations. At the heart of this cutting-edge research are two key concepts: the Wheeler-DeWitt equation and the Heisenberg uncertainty principle. The Wheeler-DeWitt equation, developed by John Wheeler and Bryce DeWitt in the 1960s, represents a major advance in the search for a theory of everything combining quantum mechanics with general relativity.